In this group project, we will be simulating some of the planning that needs to take place, similar to what engineers plan for when they are deciding how to take spent nuclear fuel rods and other nuclear waste and to transport it to reprocessing facilities or to eventually a site of permanent disposal. The problem that needs to be addressed is how to safely transport this waste because it is so radioactive. Because the decay products and the products of the fission reactions, some of them will stay radioactive for thousands, if not longer, years. The containers that are used to transport them to their final resting place, so to speak, need to be able to stay sealed for thousands of years. And this is no small feat. When you think about all the man-made structures in the world, how many of them have stood the test of time on the order of thousands of years. The containers have to be able to withstand all kinds of abuse, whether it's falling from a height, being punctured by a narrow object with a lot of force, a lot of pressure on a small area, fires, incineration, submersion in water, earthquakes. They need to be able to withstand pretty much any form of abuse that we could think of so as to protect the dangerous contents of those containers. In terms of transporting the waste, we need to think about getting it there by land. It's going to travel by truck or train, so we need to conceive of all the different possible kinds of accidents these could undergo. For transporting it by water, freighters, is it going to withstand being submerged in salt water? What happens if it sinks to a very deep part of the ocean? Will it withstand the enormous pressure of those depths? If you look on YouTube, for instance, there are some videos out there demonstrating some of the tests that actual casks or the containers have gone through, where they have taken and run trains into them at high speed, put them on the back of a tractor trailer, and run them into brick walls just to see would they stand up to such collisions, ignite them on fire for extended periods of time. So your task in this project is to design a container that's going to protect your radioactive waste while it's being transported or potentially transported. And so your radioactive waste is a grade A large egg. Sorry to disappoint those of you that were hoping for some actual radioactive waste, but there's kind of some liability issues and regulatory issues attached to that. So essentially your project is going to be to design a container that's going to protect your egg and prevent it from cracking and spilling its contents. Now, as for guidelines, remember we are designing this with the idea in mind of transporting it either by rail or by truck or by freighter, so much the same way that an engineer would need to consider those mechanisms of transport, fuel efficiency, and things of that nature. We want to sort of keep those in mind as we're designing our containers. As for the outer container, the outside part of your container must be a semi-rigid walled material. For instance, like the plastic of a 2-liter soda bottle, polyethylene, any of your other drink type containers would suffice for this. But basically a 2-liter size bottle container, that's what your padding materials would need to fit inside. The maximum dimensions are 5 inches by 5 inches by 24 inches. Essentially, again, that's a little bit bigger than the diameter of a 2-liter bottle, the 5 by 5 inches. And the 24 inches, quite honestly, is about 2 2-liter bottles stacked end to end. That's the size requirements. In terms of the weight requirement, your container, fully loaded with the egg, cannot be heavier than 1 pound. Which is 454 grams. Now, on average, a grade A large egg is about 50 to 60 grams. Obviously, there's going to be a little variability egg to egg, but when you're planning, budget about 50 to 60 grams of that limit for the egg itself. In order for your project to be deemed eligible for the competition and to be graded, your container has to meet those minimum guidelines, the size guidelines and the weight guideline. It also needs to be able to be opened easily so that after each test we can take the egg out and we can examine it. And you need to be able to reload it easily as well. So general guideline is within 60 seconds of completion of the test you need to be able to extract your egg from its container, and after it's examined be able to reseal it again in about 60 seconds. If you have it wrapped up so tightly or in such a way that it's impossible to get the egg out, well then obviously that's not going to work because we need to be able to examine the egg. Also, another guideline in terms of the padding, the outer layer of the container must be that semi-rigid walled material. In other words, you can't have padding material on the outside, so no bubble wrap on the outside, no cushioning material on the outside of the container. If you're using those sorts of things, they need to be on the inside of that outer plastic container, or whatever material you happen to use. The tests themselves, you're going to subject your container to a series of 3 tests. First is a vertical drop test. The vertical drop test will take place at the bus lobby balcony, and so that's about a 15-foot vertical drop. Next will be a side impact test, in which we will take a 1-pound weight, bottle filled with 1 pound of sand, and swing it so that it strikes the side of your container. And finally we'll have a puncture test, and this will entail dropping your container from about 3 feet onto a steel metal post. The final score for your project will be determined on how well your container performs and protects the egg payload. In order to enter the competition, again, you have to have a container that meets those size and mass requirements. But if it meets those requirements but it's not successful at protecting your egg, your radioactive waste, then obviously it didn't perform well as it needed to, so your grade for the project would be a 65. If your container meets the requirements and protects your egg for at least one of the 3 tests, then you'll get a 75. If it passes 2 out of 3, you're an 85, a B. If it passes all 3 tests, you get an A for the project, 95%. To get the 100, again, we need to think like an engineer. Not only do we want to protect our payload, but we also want to do it in a manner that is going to be cost effective for the company that is going to be shipping the materials. And so we need to think, fuel efficiency. The lighter the container is, the less the fuel costs are going to be for the company. So if you pass all 3 tests, and if there are multiple groups that pass all 3 tests, the premium for being the lightest will be an extra 5%. So again, if there's a tiebreaker, if multiple groups pass all 3 tests, the lightest of those groups will receive the extra 5 points and get the 100. If no container survives all 3 tests, then the winning container will receive an extra 5%. And again, if there's a tie for that distinction, then again the lightest one will get the 5% premium.